Hi everyone, my name is Jack Kosian, and today I'm excited to tell you about some work that we've been doing on using erasure codes in new ways to reduce tail latency in machine learning inference. This is work that was done with my advisor Rashmi at CMU and Shivram, who's at the University of Wisconsin-Madison. Machine learning inference is the process of taking a machine learning model that's already been trained and operating over input queries to generate output predictions. An example of this that you might have seen before is image classification, in which queries are images and the predictions that result from inference are a list of probabilities associated with different classes. And our net classification result is just the class associated with the maximum of these probabilities. Now, the reason that I said that we care about tail latency for machine learning inference is because inference is used to back many user-facing and latency-sensitive applications. For example, today inference is used to back translation, search, and ranking, among other applications. It's therefore important that inference be able to operate with low and predictable latencies. For example, a recent presentation from Microsoft indicated that many inference workloads have latency targets of less than 10 milliseconds. Prediction serving systems are the systems that are used for performing machine learning inference in data center and cluster settings. You may have heard of some of these systems before, like Clipper, TensorFlow Serving, and Amazon SageMaker. In a prediction serving system, we consist of a front end and one or more model instances. Each model instance is just a process or a container which holds a copy of a deployed machine learning model. Queries will be sent by applications to the front end and then load balanced across these model instances in order to perform inference and return back predictions. However, like other systems that operate in this large-scale distributed fashion, prediction serving systems face a number of potential slowdowns and failures that can lead to predictions being unavailable. There are numerous different causes of these events, including resource contention, both at the network and compute level, say due to multi-tenancy, or hardware unreliability and failures. Regardless of their cause, the net result of slowdowns and failures is inflated tail latency, which can cause prediction serving systems to miss their strict latency targets. It's therefore important for these systems to employ some means of alleviating the effects of slowdowns and failures. Now, slowdowns, failures, and unavailabilities are by no means unique to prediction serving systems. We see them in many of our systems. One popular tool that's used widely in our systems today to alleviate the effects of these events are erasure codes. For example, we see erasure codes in our storage systems to impart resource-efficient resilience against disk failures. We also see them in our communication systems to enable low latency recovery in the event of packet loss. However, erasure codes have not been widely deployed for systems that compute over data, like the prediction serving system that we saw in the previous slide. In this work, we will show how to overcome fundamental challenges associated with this goal in order to use erasure codes to reduce tail latency in machine learning inference. Our work enables one to bring the benefits of erasure codes that we've seen in storage and communication systems to this new application domain of machine learning inference. On this slide, I'd like to give you a high-level overview of the end result of our work, which is a prediction serving system that makes use of erasure-coded resilience. Under our system, queries will continue to arrive at the front end and be dispatched to model instances. In the background now, we'll encode these queries using an erasure code to generate redundant parity queries. And we'll then operate over these parity queries using a new model that we create called a parity model. Now, in the event of one of these model instances experiencing slowdown or failure, our system will be able to use the output of a parity model, as well as the output from available model instances, to perform an erasure code's decoding process in order to reconstruct this slow or failed prediction. And in this way, the system will be able to make use of erasure codes to impart resource-efficient resilience against slowdowns and failures. So now that you have a high-level idea of where we're going in this work, I'd like to take a step back and describe how we get there. To begin, I'd like to describe what we really mean by using erasure codes for machine learning inference, and why doing so is challenging. First, let me provide a quick recap of erasure codes as you may have seen them in, say, storage systems. In an erasure-coded storage system, we take data units and combine them together via an erasure code's encoding process to produce redundant parity units. Here, encoding is just being performed as simple summation. Then, in the event of a disk failure, we can reconstruct unavailable data via an erasure code's decoding process. Here, decoding is being performed as simple subtraction. Now, this same general setup can be used to encode a larger number of data units together in what's called an erasure code's parameter K. And the reason that we often like using erasure codes in our systems is because they typically enable us to impart the same level of resilience as replication-based approaches while using significantly fewer redundant resources. So how do we go about translating this erasure-coded setup to this new domain of machine learning inference? Well, it turns out that there are some differences. Under inference, rather than having disks on which we'd like to store data, we now have servers which contain a copy of some model F over which we'd like to perform inference. And rather than having data units that we would like to store, we now have queries, x1 and x2, that we would like to dispatch to these different servers in order to perform inference and return predictions. Here, I'm denoting predictions as f of x1 and f of x2. And overall, using an erasure code, we would like to be able to impart resilience against any one of these three servers experiencing slowdown or failure. To do so, we'd ideally like to be able to encode queries, x1 and x2, using a similar encoding process that we saw in storage systems. And we'd like to then generate these parity queries that we create and send them to another copy of our server. Then, in the event of one of these servers experiencing slowdown or failure, we would like to be able to decode to reconstruct unavailable predictions. This is illustrated in this slide here, where you can see that we use the available server outputs, f of x1 and f of p, to perform an erasure code's decoding process to reconstruct the unavailable f of x2. Now, by comparing our desired use of erasure codes for inference to more traditional applications of erasure codes, you see that the primary difference in this new setting is in the need to handle this computation F that's taking place both over our inputs and parity units. And it turns out that handling this computation F makes the design of erasure codes for this new setting fundamentally more challenging than it is for traditional applications. And this is because our encoding and decoding functions that we create must now hold over this computation that's going to be performed over encoded data. Now, this general idea of using erasure codes for computation-based systems relates to an area of coding theory that's called coded computation. I'm not going to go into too many details on coded computation in this talk. You can see our paper for more. But the gist of what I'd like to describe for you is that current approaches toward coded computation all take an approach of handcrafting new erasure codes. And it turns out that this is relatively straightforward when our computation F is linear, but becomes significantly more challenging for nonlinear computations. For example, current approaches in literature are only able to support highly restricted classes of nonlinear functions and require as many or more resources as replication-based approaches, which limit their practicality. As a result, current approaches toward coded computation are unable to support popular machine learning models like neural networks, which are highly nonlinear. So while erasure codes offer us the promise of resource-efficient resilience, current approaches are insufficient for machine learning inference. In this work, we propose to overcome the challenges of handcrafting erasure codes for coded computation by taking a learning-based approach to erasure-coded resilience. That is, we propose to integrate machine learning into this coded computation framework and to learn to reconstruct slow or failed predictions. So given this general goal, how do we go about introducing machine learning into our coded inference setup? A first approach that you might imagine is to learn an erasure code. That is, to replace our encoders and decoders with neural networks and to learn a code that enables accurate reconstruction of unavailable predictions. We've experimented pretty heavily with this approach and found it promising toward this goal. However, this approach comes with one main practical downside, and this is that encoding and decoding with neural networks can be computationally expensive. And because our encoders and decoders will be on the critical path of reconstructing unavailable predictions, having slow encoders and decoders will limit us in our overall goal of reducing tail latency. Based on these insights, we take a different approach in this work. We propose to use simple and fast encoders and decoders, and instead to design a new computation that operates specifically over parity units. This is illustrated in this diagram here, where you can see that we use the simple addition and subtraction encoder and decoder that we saw in our storage example, and instead operate over parities using a new computation that we call a parity model and denote as f sub p. The benefits of this approach are that encoding and decoding will now be cheap and won't add much latency to the path of reconstructing unavailable predictions. Key to the success of this approach is in the design of a parity model. Based on this diagram here, you can see that ideally what our parity model should be doing is taking in parity queries and transforming them into a form that enables this simple decoder to reconstruct unavailable predictions. So given the computation that our decoder is performing here, you can see that by rearranging the terms in its equation, the ideal output of a parity model in this example would be f of x1 plus f of x2. So if we can design a parity model that transforms parity queries into this form, then our simple decoder will be able to accurately reconstruct unavailable predictions. To design such a parity model, we use neural networks for parity models and learn to approximate this transformation function. So now that we know the structure of the inputs to our parity model as well as its desired outputs, we're ready to describe how we train a parity model. When we train parity models, we sample inputs from some underlying data set that's representative of queries that will be dispatched to our system. And we encode them together to generate parity queries. Here I'm showing encoding being performed as pixel-wise summation across these two image queries. We similarly generate the desired output from our parity model by taking the predictions that would result from inference over these inputs and combining them together. Here I'm once again showing predictions as the list of probabilities associated with a classification problem. Now that we have the inputs and outputs, and desired outputs of our parity model, training looks pretty similar to how it does in other applications. We perform a forward pass over our parity model using this parity query to generate some output. We then compare this output to the desired output of our parity model using a loss function to get some loss value. We then backpropagate this loss value to update the parameters of our parity model, and then iteratively repeat this process by sampling more and more queries from our underlying data set until a parity model has reached a sufficient accuracy. Now, the same general training procedure can be used for a number of different settings. For example, rather than encoding just 2 queries together, we could encode, say, 4 queries or a different number, which corresponds to changing in Erasure-Code's parameter k. Similarly, this approach enables us to design different encoders and decoders for this setup. For example, rather than the summation encoder that we saw on the previous slide, we could consider designing an erasure code that's more specific to image tasks, say one that takes 2 image queries and downsamples and concatenates them together into a single parity query. And in this way, this framework surrounding parity models enables a rich design space for specialization to the particular inference task at hand. Now, one caveat that comes into play due to this, or by using machine learning for this approach, is that we will only be able to reconstruct approximations of unavailable predictions. That is, we're no longer guaranteed that the results of decoding will be the exact predictions that would have resulted normally. We note, however, that for our target application domain of machine learning inference, this is often considered appropriate. In particular, this is often appropriate because the predictions that result from inference themselves are to some extent already approximations. Furthermore, any inaccuracy that's going to come into play due to this approach will only be incurred when predictions would otherwise be slow or failed. Within this setting, previous work has motivated that it's often preferable to return slightly less accurate predictions rather than those that will miss their particular deadline. So now that we've described for you how parity models work, we're able to circle back to this slide that we showed at the beginning, which is the overall system that we've built using parity models to enable erasure-coded resilience. And we use this setup when we evaluate parity models. In evaluating parity models, we aim to answer 2 main questions. First, how accurate are the reconstructions that result when using parity models? And second, by how much can parity models help in reducing tail latency? On this slide, we'll compare the accuracy of the original model that's been deployed for inference to the accuracy of the reconstructions that result when using parity models. On a number of different image classification and speech recognition data sets, we find that the reconstructions that result using parity models are at most 6.4% lower in accuracy compared to if the original model was available. This is a promising result considering that current approaches to coded computation are unable to support even simple neural networks. And I want to remind you that the accuracy of parity models is only going to come into play when predictions would otherwise be slow or failed. So in reality, this potential drop in accuracy is only going to affect those queries that would otherwise have been at the far end of our latency spectrum and for which we can now recover with much lower latency. For example, assume that a system had 10% of predictions being slow or failed. If we use parity models in this system, it would result in at most a 0.7% lower overall accuracy compared to if the original model were always available. So this enables parity models to return predictions with high accuracy. In evaluating the tail latency reduction that results when using parity models, we showcase parity models in the presence of resource contention. Compared to approaches that make use of the same number of resources as parity models, we find that parity models can lead to a significant reduction in tail latency while maintaining the same median. And this enables parity models to return predictions with highly predictable latencies. Now, what I've talked about here is only a subset of the evaluation that we've considered in this work, and I encourage you to see our paper for a more detailed evaluation, where we consider different encoders, different inference tasks, different code parameters K, and different baseline approaches. To summarize our work, within this work, we've shown how to overcome fundamental challenges associated with using erasure codes for computation-based systems through a learning-based approach to erasure-coded resilience. The result of our work are parity models. Parity models enable accurate reconstruction of unavailable predictions that result from neural network inference and enable one to reduce tail latency in the presence of resource contention. And as a result, our work enables one to bring the benefits of erasure codes that we've seen in storage and communication systems to this new domain of machine learning inference. If you're interested in learning more about our work, I encourage you to come talk to us at the poster session, to read our paper, and to check out our code and other resources which are made available at these links. Thank you, and I'd be happy to take any questions at this time. Yeah.
Hi, this is great work. I'm Jun Song from Princeton, and I have a question with like a general setting of like your problem. Like you are aiming at a query which related with K models, right? Like K different models.
They're the same model. It's replicas of the same model.
Okay.
Those K, yes.
Yeah, but it seemed to me like when you like train model, like you need to combine like using the different model. Like if it's okay, maybe let's talk about afterwards.
Okay, sounds good.
A little bit
Thanks.
hard to describe.
No worries.
Ken Berman, Cornell University. I like to talk. I want to question something you said on slide 104. And by the way, it's kind of awesome that you're on slide 112. But anyway, you commented that if 10% of the time you kick over to the parity-based model, then the actual loss of accuracy was a tenth. And I'm going to question that. It seems to me you've actually ended up with a modal solution that 10% of the time is off by 6% and 90% of the time has some much higher accuracy. And I'm wondering if for tasks that are time critical, like a self-driving car trying to avoid hitting pedestrians, a modal behavior like this with a violently higher inaccuracy 10% time, it might be more important to characterize it as behaving that way and slightly confusing to the potential user if you said, oh, it's just a tiny bit less accurate.
Yeah, I think I heard most of it. But yeah, thank you for the question. I agree that for certain applications like self-driving cars, for example, something that, in some ways we're trading off accuracy a little bit for latency, maybe this isn't the best approach if you're in a safety critical application. For other applications though, I think it's been shown that there's certain cases where it's better to return something that's slightly less accurate, for example, or rather than missing a deadline. For example, ad serving is one example of this, where it's better to show some ad that's at least slightly relevant rather than showing no ad at all. So I agree though that there are certain application domains where the trade-offs that we make in this work might not necessarily be appropriate. I'm sorry if I'm mischaracterizing your question.
No, that's a good answer, and it's exactly my question.
Okay, thank you.
Hey, Steve Hand at Google. I'm curious about your setting. You seem to have multiple identical models, and the query needs to talk to K of them. Why would that be the case?
So the setting here is that, like any, say, web service, right, where you might need to be operating with at high query rate, right? Typically the way we operate in these scenarios is in a scale-out manner, where we take, multiple copies of the same computation we want to perform and place them on separate servers, say, and we load balance queries across them. So these different queries that are coming in are, say, from different users, right? So X1 might be sent by you, X2 is sent by me, and maybe to keep up with incoming query rate, we load balance these across different servers. So that's the setting that we're operating in.
So you're trying to jointly code queries from distinct users for different topics?
But they could potentially be different users, yes.
Okay, thank you.
Jainil Gandhi, VMware Research. My question was, so in the parity case, when you are constructing parity, are you using X1 and X2 all combinations possible to do that?
Yeah, this is a really good question. So this comes down to when we're training a parity model, right? How do we form the combinations that we use when training? So it's actually, if you think about it in an abstract case, suppose we have a data set that has n samples in it, right? Now when we go to train a parity model, we're choosing k different, you'd say 2, right? Like you said, 2 different things. Now our effective data set size is n squared, basically, right, of possible combinations that we could be using. And this is going to quickly blow up as we, increase that number there. So currently we take just a pretty simple approach of just randomly sampling different things from this data set and to combine together. But I think that a more principled approach might help in maybe closing the accuracy gap a little bit.
Also, do you read the parity model on every query?
Sorry, do we use the parity model on every K, you think?
Yeah.
Yeah, so we, for K queries that come in, we encode them together and send it out to a parity model. Whether we use that result from a parity model or not is going to depend on whether the other queries were slow or failed during computation.
Sorry, folks, we are out of time.
Yeah, we can talk offline. Thank you.
Right, thanks.